the bottom of page 17, something very closely related to the remainder theorem is something called the factor theorem. The factor theorem says the same thing as the remainder theorem. You can find the remainders by plugging in the number. That's always the remainder theorem. When the remainder is 0, as is the case in the black one and the blue one, when the remainder is 0, we found out that this was a perfect factor, that we have started to factor it completely. And this is going to be our goal, is to try to figure out how to factor things when they get bigger. So if we can find a number that when you divide makes your remainder 0, you will know it's a factor. And our goal is going to be to factor things completely. So we're going to start with this example, and we're going to test these. Are these factors or not? So for part A, because it's a small number of 1, I like using the remainder theorem and saying it is easy enough to plug in -1 to figure this out. If I plug in -1, I would get -1 cubed minus 6 times -1 squared plus 5 times -1 plus 12. And now it's just the mental math. A negative cubed is still negative. A negative squared is a positive 1 times that -6 will be -6. 5 times -1 will be -5 plus 12. So with a 1, it is not hard to find whether or not the remainder is 0 or not. And because the remainder is 0, the factor theorem tells us that x plus 1 is a factor. And we're very excited, because if something is a factor, that means we can start to factor. Okay? In fact, if you wanted to factor it, you would need to write your division statement, so it makes sense to do the synthetic division. Right? Remember the synthetic division, we write our coefficients, 1, minus 6, 5, and 12. If you're dividing by x plus 1, we put the opposite sign out in front. Bring down your number, multiply, add. Multiply, add, multiply, add. And you should get the same remainder with synthetic division. So another advantage of the synthetic division over the remainder theorem is not only do you get the remainder with synthetic division, but you are ready to write your division statement. Oh, I would lose marks on this one for not first doing this. Okay, I used p of something. I should let p of x equal, and put that in brackets so that I can use short form when writing. What this allows me to do is I can write my division statement for this question. And my division statement would look like this. So p of x is equal to, we divided by x plus 1, and we were left with x squared minus 7x plus 12. Now, before we get to b, I would just like you to leave a little bit of space. We're going to come back and write something more underneath this in a bit. But we're going to go next to b. Now, since b is dividing by an x minus 3, that's a bigger number, I might right away try to find my remainder with synthetic division. My numbers are going to be the same, 1, -6, 5, and 12. This time I'm dividing by x minus 3, so out in front I put the opposite sign. You guys get a 15-second head start to finish the synthetic division. Give me more than a 15-second head start because I made a mistake. There we go. Bring down the one. I wrote it through. Again, we get a remainder of 0. So this means that would be right. So we now know that x minus 3 by the factor theorem is a perfect factor. And I can write my division statement this way. That p of x could have been written as x minus 3 multiplied by x squared minus 3x minus 4. And again, we'll leave a little bit of space here and go to part C. In part C, we're dividing by x minus 4. So once again, 4 is a huge number. So I would probably go to synthetic division. My coefficients are still the same, 1, -6, 5, and 12. A 4 would go out in front, and once again, I'll give you a 15-second head start on your synthetic division. Once again, we got a remainder of 0. This is so exciting. So we could have written our division statement like this. X minus 4, and we're left with x squared minus 2x minus 3. And again, we're going to leave a little space there for later. We have 1 left to go. This time we're dividing by x plus 4, so I put a minus 4 out in front. And again, I'll give you 15-second head start. Are you feeling you're getting good at this synthetic division? Is it super hard? Not too bad. That's kind of nice. We're almost done this unit.
Really?
It's that quick. Well, we have basically 2 concepts. One is this factoring stuff, and the next is using the factoring stuff to help us graph.
How will the test be?
The same as all the others. Yeah. We're about half done. Okay. How'd you do on this one? Did you bring down the 1? Multiply, -4, add, -10. Multiply, 40, add, 45. Ooh, we had a little bit of mental math to do here. Anyone can get -1 180. Did you get a remainder? This is the first one. That's not a factor. So if we wrote our division statement for this one, you'd have x plus 4, x squared minus 10x plus 45, and then you'd have to add your remainder of negative 168 at the end. Factoring, though, is important because one of the questions that we often ask in mathematics is to solve. Can you solve when this is equal to 0? That's a common mathematical question. Solve an equation. And we learned with any equation that was x squared, you could rearrange it to make one side equal to 0, and then factoring or the quadratic formula helped you solve it. But we're going to get into questions that say, could you solve an x cubed equation? Well, we would need a technique to factor that. And what we've done here is we've used our synthetic division and our remainder theorem. If we can find a remainder of 0, then we can write our division statement. And our division statement is starting to factor. In fact, I could factor this completely because now this is a quadratic. And x squared minus 7x plus 12, if I factor that, it would have to be x and x. Two numbers to get me 12 would be 4 and 3, and if they were both negative, I would get minus 7x. And now I've factored that one completely. Look at the second one. This one had no remainder, so it's a starting factor. Can I factor this completely? Well, if it has to be x squared, it would have to be x and x. And to get a 4 and a 3 would have to be 4 and 1. The 4 would have to be negative, the 1 would have to be positive. And I would get x minus 4 and x plus 1. And the third one where there was a remainder of 0, I could take this quadratic and see if I could factor it completely. Look at this, it's going to be x and x, 3 and 1. The 3 would have to be negative, the 1 would have to be positive. And that one's factored completely. And I want you to notice that in A, B, and C, when we factored it completely, put my highlighter on it. This is factored completely. This is factored completely. What do you notice? Are those the same? Just in a different order, right? Are they the same with the first one? Are all the factors the same? Yes. Does it make sense that if you have x squared, you can have two factors? Because you have an x and an x, giving you the x squared. When we have an x cubed, you can have up to 3 factors. Does it make sense that you add a 4th factor, you're going to have a problem because all of those x's would make an x to the 4th. Now, if you went back to grade 9 and had to multiply this out, in grade 9 you would say, pick 2 of them to multiply first. So I would choose these 2 just because I can go up and say, that would give me this. And then when I have those 2, I can multiply that out and do, like, you have, remember all of these arrows that you'd have to do to multiply it up? I mean, with quadratics, we sometimes use the word FOIL. Multiply the first, the outside, the inside, the last. This is like FOIL, like it's, we could make a new acronym for it, a whole bunch of little O's and big O's for the little outside, the big out, I don't know. But the important thing to notice is that the first ones, and all my first ones are x, they still, here I'll even scroll up. Oh, I don't know if I can scroll. I'll circle this. You see that your first ones still match up to the first one there. x times x times x still gives me x cubed. But more importantly is to notice that your last ones, 1 times -4 times -3, they give me 12. That is still true. Same thing as factoring with 2. Your last ones multiply to give your last term. When you have 3, your last ones still multiply to give you your last one. So if I had added, with that in mind, which are factors, and if the last one was x plus 7, you would have to do almost no work at all. Is it going to be a factor? Absolutely not. Why? Because 7 never works out to be 12. It's the same thing like if I got you to factor this, and someone says, I'm going to start with x plus 13. You'd be like, what are you doing? That makes no sense whatsoever. Like, why use 13? That's going to be bad, because there's nothing, 13 times nothing makes 24. That's a bad option, because our last one has to work out to that last one. And this is going to be our hint for factoring, because what we're going to get is we're going to get questions that look like this and say, factor this completely. You would never say, I'm going to start with x plus 7 and see if it works. That's a dumb choice, because 7 never makes 12. What are good choices? 1, 3, 4, 2 would be a good choice. See, you don't know at the beginning which ones are going to work. So usually people start with 1, because this they can do really quickly with mental math for 1. I would try 1, and I would try -1. Those would be my first two. I probably wouldn't do synthetic division with 1 and -1, because this is pretty quick. If it works, then I do my synthetic division, and once I find 1, I can write my division statement. And if my division statement comes down to a parabola, then I can just finish up and keep going and factor normal. So this is going to be how we can factor completely. Okay, circle questions 10A and 12. I want to make sure you look at 12 and do some problem-solving strategies. So I put a star beside that one.